It's important that when we look at these problems that we define our variables. So here, what does x represent? Number of CDs, right. So up top, that represents number of CDs. When we hit later chapters, if you don't define your variables, you're going to lose some points. So make sure that you define them, telling me what they mean. What does the x represent here? Video games. Okay, questions on those two? So hopefully none of you are playing games on your phone right now, and we'll start the next slide. Okay. We are continuing notes, so this is not a new section, not a new essential question. We're going to look at two possibilities for solutions that you can have for your linear equations. One possibility that we've talked about before is that you can have one solution. You solve for x and you get a number. Another possibility that you've probably dealt with in the past is not having a solution. Not every equation has a solution. In that case, we denote it as such, no solution, or we write no solution. Okay, this is the shorthand. Mathematicians don't like to write a lot, so they use a lot of shorthand. Now, the other type of solution we have is a bit unique. It's called infinitely many solutions. Now, it says equations do not always have one solution. An equation that is true for all values of the variable is an identity and has infinitely many solutions. One thing that students always mistake is they say, is an identity the same thing as infinitely many solutions? No, they're separate categories. An equation can be classified as an identity. And if it is classified as an identity, then it has infinitely many solutions. Does that make sense? So it's kind of like saying you're a boy and you have red hair, and you're trying to equate boy and red hair. But red hair is just a characteristic of that boy, or whatever. Okay, so looking at this bottom equation, how do I go about solving it? I distribute that sucker, so I'm going to go ahead and distribute. Thank you. So I'm going to take 3 times 5x, 3 times 2. I get 15x plus 6 equals 15x. What's going to end up happening with the 15x's? Yes. They're going to cancel each other out. That's beautiful. Couldn't have said it better myself. They cancel each other out and you get 6 equals 0. Well, I don't live in a parallel universe where 6 equals 0, and neither do you. So this is not true. And because it is not true, it is no solution. Unless you're Rick and Morty, and then it might be. But. Okay, questions? All right. This is an identity. This equation is an identity because when we distribute the 2, we get negative 8y minus 2 equals negative 8y minus 2. Well, golly gee willikers, they're the same. So it's an identity, and all identities have how many solutions? Infinitely many. So I'm going to just abbreviate that IMS. And you can too. Questions on that one? Concerns? Comments? All right. So you can practice these. Give it a try. You're welcome. I just want you to flex your math muscles. We have our times, upstream and downstream. We know that downstream takes less time because we're traveling 2 miles per hour faster. Now, looking at all of that, what can I do with it? Well, I have a formula. What's my formula again? Dirt. Distance equals rate times time. So I'm going to write that down. Well, I have 2 of those equations. Why? Why am I going to look at 2 distance equals rate times times? Because on the way there and on the way back, you're taking a different amount of time. You're taking longer on the way there, and you're traveling faster and taking less time on the way back. Does that make sense? But all together, you're still traveling the same distance, right? Up and downstream. So if you're still traveling the same distance, well, let's see. What can I do to solve for something? Maybe I can set them equal to each other because you're going to be traveling the same distance, so they're going to be set equal to the same thing. And if they're equal to the same thing, then that means I can set them equal to each other. Yes? You seem to be struggling a lot less than my other classes. Do you really get it?
Yeah.
All right. Well, give it a try. Let's see what you come up with. So, here we are traveling on our boat on the Mississippi River. And I'm going to create this equation to solve for the rate because I don't have a rate. I can't find a distance if I don't have a rate that I know, right? I do know a couple things about that rate, so I'm going to apply it to the equation that I have. I know that going upstream, let me do this in black here, I'm going to take whatever my rate is times 3.5, and I'm going to be equal to a distance, correct? Does that make sense? Because I'm traveling the same distance, I can set them equal to each other. So downstream, I'm going to be traveling a certain rate, and I'm going to take 2.5 hours, and that rate is whatever my previous rate was plus 2. Does that make sense? Yes? Yes. Okay. So now I'm going to solve for the rate. I get 3.5 r equals 2.5 r plus 5. Well, now I just solve, subtract those r's, and I get r equals 5 what? Miles per hour. So you're on this boat and you're traveling 5 miles per hour. And then upstream you're traveling, or downstream you're traveling 7 miles per hour. Does that make sense? Well, they didn't ask me for the rate. They asked me how far upstream. So it takes you 3.5 hours and you're traveling 5 miles per hour. So what's 3.5 times 5? That's 17. So you travel a total of 17 miles upstream. Did that make sense, or was it gobbledygook, as my old teacher would say?